Assalamu alaikum, hi everyone. Welcome to our webinar, Hydraulic Fracturing Evaluation. So I am Abdullah Abdurrahman. I am Reservoir Solutions Team Lead, and we will have just 5 minutes presentation about reservoir solutions and introduction for the biography for Mr. Muhammad. Then we can start our webinar. So about Reservoir Solutions is a company specialized in providing technical studies and courses for oil and gas companies and professionals. The company incorporates many professionals with diverse technical background related to oil and gas exploration and production. Our services, we are providing technical reservoir studies, field development planning, reservoir static and dynamic modeling, economic feasibility studies, technical support for academic researches like PhD and master degrees. So if you are PhD or master students and you need some support from us, so we can provide you with the technical support that you will need. Also, we are assisting in writing technical papers and publishing it. Also, we have technical petroleum courses that will be provided by industry experts. Also, we are providing mentorship programs. For mentorship programs, if you need to focus on some topic, like if you wanted to have a private course related to reservoir modeling, related to nodal analysis, related to production engineering, related to hydraulic fracturing, or any topic that related into oil and gas, so we can provide you with a private course with an instructor with a high experience related to this topic. So before going to introduce Engineer Muhammad, just I wanted to provide you with an introduction to our upcoming courses. We have 2 upcoming courses. First, the hydraulic fracturing, pre-job design, execution, and post-job evaluation. So that course will start on 25th of August. Okay, so we have about 12 days, then we will start, inshallah. In all our courses, we are provide lifetime access to recorded sessions. So if you have any difference in time zones, so don't worry about that. You will have lifetime access to the recorded sessions. Also, application datasets, you will have some datasets to apply using the software. Application-based workshop, our workshop is practical 100%. Also, we are providing the course material like lectures, PDF, Excel sheets, and so on. Also, you will have open discussion with the instructor during and also after the course. So if you have any question related to the course after the course period, you can ask the instructor. At the end of the course, you will have a certificate with online identification. So all of that package will be granted for all of our courses. For the course of the hydraulic frac, by the end of this course, you will be able to know the application for the hydraulic fracturing, to select the candidate for hydraulic fracturing, understand the hydraulic fracturing operation sequence, the equipment needed, how to select the fluids, proppants, and equipment. Also, how to model or how to make geomechanical model related to your reservoir. Also, you can design, you can make the diagnostic plots that needed for the hydraulic fracturing, like the mini frac design or mini frac analysis, and all the other pumping diagnosis plots. Also, you can make QA, QC for the hydraulic fracturing job, and all the other diagnosis for the evaluation for the hydraulic fracturing. All of that will be done on software to have practical industry standards. Okay, the price of this course will be about $35 for students. So it will be very good opportunity for students and also for professionals. The professional price is only $50. Okay, if you wanted to register for that course, I will send a link for registration into the Zoom chat. So that was for the first course that will start on 25th of August. The second interesting course that we will start, inshallah, in September, in 10 of September, it will be 2 weeks hands-on experience workshop related to borehole image, FMI or OBMI, borehole image processing and interpretation. So if you wanted to make interpretation and processing for the FMI log or OBMI log, you will have that chance after attending of that course. Okay. Also, the same package for the course, lifetime access, datasets, practical workshop, course material, and also certificate and with the instructor. By the end of that course, you will be able to know the application for the FMI, also do processing and quality control, do manual depth picking, interpret reservoir structure and stratigraphic that will be needed for the structure modeling for the reservoir. Also, porosity evaluation, texture identification for the carbonate reservoir, fracture characterization and interpretation, thin bed evaluation by texture identification and sand counting, to processing and interpretation for the acoustic imaging. Also, we will have acoustic imaging into our course. Okay, so all of that you will enjoy by the price of that course. For students, it will be only 60 USD, and for professional, it will be 80 USD. Okay, the course is very cheap related or compared to the other organizations. Okay, thank you. So that was about our courses. For our today webinar, Mr. Engineer Muhammad for Engineer Muhammad is graduate research assistant at Houston University in USA. Also, Engineer Muhammad is a senior petroleum engineer with a decade of working experience with Khalda Apache GV in Egypt. Also, currently, Engineer Muhammad is leading the hydraulic fracturing team at Khalda Apache joint venture since 2016. Engineer Muhammad experience is in convention and also unconventional reservoirs, also with multi-stage massive hydraulic fracturing job, projects in design, execution in field, and also evaluation. Engineer Muhammad published multiple papers with SPE, OTC, ARMA, Petroleum and Coal Journal. For our webinar rules, as usual, if you have any question, please drop it into the Zoom chat. Mute your microphone and camera. In case that you want to have a certificate for the attendance, fill in the form that will be sent into the Zoom chat. For our upcoming courses and webinars, you can join our Telegram channel to enjoy attending that events. If you have any concern, you can contact us via our mail and also our WhatsApp. All of our contacts, also the links to register and to view the course content will be sent now on the Zoom chat. Okay. Thank you all, and Engineer Muhammad, you can start, inshallah.
Yeah, can you see my screen? Can you see my screen?
Yes, we can see.
Hello, everybody. I am Muhammad Adil Gabri. Today, we'll talk about the hydraulic fracturing evaluation during the treatment and after the treatment. To understand, the main idea of hydraulic fracturing is to conduct a treatment to enhance the production of the well. So we did a lot of jobs in design and to know the proper design and to conduct the treatment. But the main problem is due to the depth of investigation and the depth of treatment that covered by hydraulic fracturing is very large. So it's very hard to evaluate, to understand what really happened in the earth during hydraulic fracturing. So hydraulic fracturing evaluation is a key part for hydraulic fracturing industry to understand what happened during pumping hydraulic fracturing job due to its a massive fluids and massive amount of proppant pumped in the formation. So we need to know what is the fracture that's created in the formation, and does this design really created in the formation or not. The fracture geometry, we need to, before we understand the hydraulic fracturing evaluation, we need to understand the fracture geometry. For any simple hydraulic fracturing, we need to, if we need to simplify hydraulic fracturing, the hydraulic fracturing consists of width, which contribute mainly in production increase, and XF, which is the length of hydraulic fracturing inside the formation, and the height is the height of hydraulic fracturing that cover the. We need to ensure this height cover the base zone or not. That's, and this fracture is filled with proppant with specific conductivity. So we need to know what is the conductivity that's created in the formation, to know the what happened in the formation during the treatment and after the treatment. The XF, the hydraulic fracture half length and fracture conductivity, is what is created in the formation, and what is the main contribution of frag during the post frag production. To understand the fracture propagation simply, we can make an analog for simplification. Let's imagine you blow a balloon with your mouth, and that's typically what happened in during the fracture propagation. We pump fluid, like in this case is air, but in hydraulic fracturing is fluid. So you pump, and with pressure you pump rate with, and this rate increase the volume of the balloon to make the fracture, like the fracture. So the fracture geometry, in which is the volume of balloon, is a difference between the inner pressure and the outer pressure of the balloon, and this is the fracture analog to the fracture geometry. Also, during the treatment, we need to keep the net pressure high enough to create the suitable geometry during and keep the width and keep the width of frag open to place the proppant placement. Also, you will get some resistance if this distance is larger, so due to the frictions. So this friction will decrease your net pressure. At the end, the shape of fracture geometry depends on the net pressure, how the amount of pressure that you bump in the balloon, or you bump in the formation, the amount of pressure more than the closure pressure or the minimum horizontal stress in the formation, or the stress of the formation that you act against during the placement. Also, it depends on the formation properties, and also depend on the leak rate and many factors. Also, important point is what happens if you think in this analog, what has happened to the balloon material. So you can imagine that you can figure out that the balloon material is under tension. So hydraulic fracturing is the same. During the the treatment, during pumping hydraulic fracturing, what happened to the well bore diameter is tension. Also, if the balloon has a hole, so it will be harder to fill the balloon. So it's the same during the treatment of hydraulic fracturing. If you pump hydraulic fracturing and there is a leak or loss in net pressure, so it will cause it will be hard to create the required hydraulic fracture geometry. So the main concept that we need to understand to evaluate the hydraulic fracturing during the treatment is the net pressure. What is the net pressure? Simply is the amount of pressure that increase more than the minimum horizontal stress to create the hydraulic fracturing. To understand that, we need to imagine set concept of hydraulic fracturing is to pump with rate. So we don't pump pressure, we don't put pressure, we pump rate like you pump in a pipe. Then, due to the resistance of the formation, due to its low permeability, or it can't handle this high rate, the pressure increase, and this pressure increase more than the fracture pressure, then it break. So the fracture is created due to the rate, not the pressure. Due to we apply the rate and the resistance increase, then the pressure increase more than fracture pressure, then it will create a hydraulic fracture. So net pressure simply is the pressure inside the fracturing if we removed the effect of what make the formation close this fracture. Because we open this fracture and the formation tends to close this fracture to reach to the equilibrium. The difference between the pressure inside frag and the closure pressure, or the minimum principal stress that tends to close the frag is called net pressure. To calculate this net pressure, simply we pump the fluid, and we can measure the wellhead pressure. If we added the hydrostatic head, the hydrostatic head on the well, on the wellhead pressure, and removed the effect of frictions, in all frictions down to the formation, including perforation friction, pipe friction, neural bore friction, or entry friction, we can get the pressure inside hydraulic fracturing. So the pressure inside hydraulic fracturing is wellhead pressure plus hydrostatic pressure minus all frictions that we needed to avoid, or that we needed to increase till open the hydraulic fracturing. This pressure inside hydraulic fracturing this pressure inside hydraulic fracturing minus the pressure or the stress that tends to close hydraulic fracturing is the value. This difference in value is called net pressure, and this is the main contribution of fracture geometry. All the fracture geometry is due to net pressure, and all the fracture simulator can understand and calculate from for the fracture geometry is calculate the geometry based on the net pressure. The main loss in net pressure is, the main loss that cause decrease in net pressure is the friction. So if the friction increased, that will take from my net pressure, so the fracture will close. To understand well net pressure, you need to understand that we have two types of friction. Pipe friction is due to the friction in pipe, and perforation friction is a perforation friction due to we have perforation, multiple perforation, and this perforation cause frictions, fluid frictions. So the pressure that we open the frac with, it decrease by this amount. So we need to apply to get pressure higher than this value. And narrow bore friction is due to the fracturing fluid orient to be perpendicular to minimum horizontal stress to make the fracture propagation. So this orientation is and this alignment of fracture of fluid path cause frictions called narrow bore frictions. Also, for hydraulic fracturing to create a fracture geometry, simply we need to understand that net pressure net pressure relation with the stress difference is the main control of fracture height. So if I pumped with net pressure 1000 psi, for example, how the fracture will be how the fracture propagate in height? Simply, there is old rule of thumb and the study based on experimental study is any net pressure can break the stress difference between two formations if it reaches to 50% of the stress difference, and once it reaches to 70% of this stress difference, it will propagate and it will break the barrier. It's very important to understand that we create net pressure, and this net pressure will struggle and will compete with the stress difference, and this stress difference between two formation is very low and can't control this net pressure. This net pressure will cause the fracture geometry propagate in the formation. So if I bump it in this sandstone and this net pressure more than 50% of stress difference between the shale and sand, it will cause fracture propagation in shale and until the net pressure is consumed to with the fracture geometry. So why we need to understand the net pressure? Simply because net pressure is related to fracture geometry, fracture height, fracture width, all the fracture geometry created by net pressure. So we need to understand the net pressure analysis to understand the fracture geometry, the real fracture geometry during design, during on-site analysis or post-frac analysis. Net pressure, as we said, is the main concept of fracture geometry and the fracture propagation. If there is any net pressure created in the formation, so there is a fracture with fracture width, and the width is related linearly with the net pressure. So if I had a hydraulic fracture job, there is pressure up and down, and I have a plot of hydraulic fracture job, and there is pressure going up and down and during the treatment. To understand what happened during the treatment, we need to convert this pressure to net pressure. How to convert this wellhead pressure to net pressure? Simply by the equation is if this wellhead pressure, you can add hydrostatic pressure and remove the effect of frictions, near bore friction, by friction, and near bore friction, by friction, perforation frictions. All these effects removed from the pressure and add your hydrostatic, then remove the closure pressure to understand how the net pressure is created during the pumping. And from the net pressure, with time, you can understand how the fracture propagates. Also, to understand the fracture propagation, the fracture initiation starts from the weakest point in the minimum horizontal stress. So there is minimum horizontal stress in the formation due to the difference in formation properties. The main point is the fracture initiation happen in a point where is the minimum horizontal stress is the minimum, then start to propagate like to propagate and start to increase in height. So the net pressure in this time starts to decrease because we didn't cover the whole base zone yet. Then when we reach the barrier, when we reach the shale above, or the stress difference that can control this net pressure, the fracture propagation starts to propagate in length, so we can get increase in net pressure. So it now the minimum the stress difference control the net pressure, so net pressure tries to create the fracture geometry in length. Once the net pressure increase more than the stress difference between the base zone and the barrier, so the net pressure invade the barrier and create the fracture, create a fracture in base zone in the barrier, and it can be seen as height growth. So a technique called Nolte-Smith technique, simply it's a magnification of the effect of net pressure with time. So Nolte-Smith set a technique with some assumptions that it works only with net pressure, with the pressure. So it assumes constant injection rate, continuous fracture propagation. So we create a fracture and it propagates, it doesn't stop during the treatment, and it needs the formation closure stress. Formation closure stress is a stress that tends to close the fracture against the fracture propagation. Nolte-Smith is a real-time analysis. During the pumping, you can understand how the fracture propagates. Nolte-Smith technique and get the fracture events, like if for example you have screen out, you have probant bridging in the formation, so you pump a probant and this probant doesn't go too deep in the formation, or you have high propagation, so your net pressure decrease and your fracture geometry is not efficient and created in the height, not in the length as you want or as you design. So it detects how the fracture geometry is created during the treatment. But the main disadvantage of Nolte-Smith technique, it needs the formation closure stress, and as it's hard to understand a fracture geometry, so it needs more experienced people to understand what happened in the formation. Nolte-Smith technique simply is a relationship log between net pressure and injection time, assuming injection rate is constant, and we know the fracture closure pressure, and we assume the fracture propagation is continuous during the treatment. First, if we saw at the start of the pumping, start of creating the fracture propagation, so the slope, you can find the slope of log net pressure with time to be between 1/8 to 2/4. The slope that means that we create a fracture, but still we didn't reach the stress difference between the base zone and barrier. Once it starts to stabilize, so we now start get propagation in height at normal fracture propagation. The slope is 0, and we need to keep monitoring this pressure, this slope during the treatment in the frag van. Then if the net pressure drops, so this means the negative slope means the net pressure invaded the stress barrier, and we have unconfined the height. And this is a very risky situation, because simply net pressure, which is the main source of fracture width, and fracture width is what allows us to place the proband. So during the treatment, if net pressure drops, the widths drop, and the fracture widths close, so it may cause proband screen out. Proband screen out can be identified also from Nolte-Smith by, if we observe the net pressure slope to be 1, so this fracture is filled, and we now we don't have any fracture propagation in length, and we are filling our hydraulic fracturing geometry with proband. And if the slope increased more than 1, that means proband bridge around the neural bore, and there is a screen out in the formation, and we need to take any action to avoid or remove this screen out. During the treatment, when you are in the frag van to watch the net pressure up and down, and you estimate the fracture geometry from what happened in the frag van, you understand. For example, this fracture, if you saw, for example, net pressure drops, so your fracture geometry has more height than the design, so the fracture length is expected to be lower. So during the Nolte-Smith technique, a Nolte-Smith analysis of fracturing pressure during the treatment, you have a rough figure of the fracture propagation and the fracture geometry, but the real analysis of fracture geometry conducted after the treatment, after the pump shutdown. There is 2 ways to evaluate your treatment after job. There is tools to measure the fracture geometry and to understand the fracture performance, and analysis. The analysis technique is something to do in the field and get the data and do the analysis. The main analysis technique for the post-fracture evaluation is pressure transient analysis. You flow the well, then shorten the well to get the flowing buildup period, pressure, and rate, to do well test analysis, and we'll discuss it in minutes. The second analysis is the production data analysis. You design the frac, you expected to produce with certain production, and you expected to get this pressure during the design, during the treatment design, and this pressure, and from what we get from the field guys is the production data analysis is the well produced by this rate for this time, and you get the treatment pressure and rates, and during the treatment analysis of production data analysis and the fracture treatment analysis, it's combined together to compare what really happened in the treatment and after the treatment compared to your design. Another way is the measurement tool, is something that you measure the fracture propagation. Simply, fracture height can't be measured except the temperature log, and the fracture half length is a way to measure is measured by the microseismic monitoring. The contribution of each frac can be measured using tracers. After we conduct hydraulic fracturing and create a hydraulic fracturing around a well, the first period in post-frac production is linear flow, where is only flow from the first period, and the start of fracture propagation of fracture production is linear flow from from fracturing. It can be identified as wellbore storage, but it's only flow from the hydraulic fracturing itself. Once we get contribution from the reservoir, so we have bilinear flow. So this linear flow from the formation and linear flow from the fracture, we call this flow regime is bilinear flow regime. Once the formation get engaged in the production, so the formation become the main of the fracture propagation, of fracture production. That means we get formation linear flow, and the fracture linear flow is neglected, can be neglected, because the main contribution is from formation linear flow. And once we get contribution from all the reservoir, and contribution from the bounds of reservoir thousands feet away. So the fracture, we can get radial flow regime around the fracturing. This main understanding for post-frac production is a source of when we do pressure transient analysis and we flow the well for certain period at constant rate, then shut in to get the pressure transient analysis and the build-up after hydraulic fracture, after production period, to get the shut-in, the pressure shut-in time. We get the analysis of the pressure and rate of pressure transient analysis of flowing build-up period, and do our analysis by the well test analysis. More details can be get from well test analysis course, or we simply we get the log delta B, which is the pressure difference between any point and the start of shut-in, and we get the derivative of this delta B and plot as a log with the delta T starting from shut-in time. From the pressure transient analysis, we can figure out from the slopes from the delta B and from the derivative, we can get the fracture geometry. For example, the bilinear flow in this is our examples for pressure transient analysis after hydraulic fracturing. For bilinear flow, we can identify it from slope 0.25, and from the bilinear flow we can get the dimensionless fracture conductivity. And as you know, dimensionless fracture conductivity is the permeability of the fracture multiplied by length of hydraulic multiplied by width of hydraulic fracturing over the permeability of the formation multiplied by XF, which is fracture half length. So if you get CFD and you know the XF, and you know the permeability of the formation, and you know the width of hydraulic fracturing, you can identify the fracture permeability, or you can, if you don't have the width, you can identify the fracture conductivity. So from bilinear flow, we can identify the fracture conductivity, and from radial flow, you can identify the formation permeability, which can be used to get the fracture conductivity from the dimensionless conductivity. Also, from linear flow period is related to, which is can be identified with slope 0.5. You can identify the fracture half length if you know the formation permeability. So as a conclusion, from the pressure transient analysis, you can figure out the flow regime of each type of each period in the post-frac production, and identify the properties of the fracture, which is the fracture conductivity and the formation and fracture conductivity and fracture half length. From production data analysis, simply during the design process, we as a frac design, we estimate the fracture performance after hydraulic fracturing. So when I go to frac a well, so I have a plan that after frac should, for example, produce 1,000 and drop and to stabilize at 500 barrel per day. So when this design is conducted, I compare what I expected with what I really conducted, by compare the production curve or the flow rate with time, with the actual one, between the design and the actual one. But the main question is, what is the fracture geometry that produced this actual production? So I need to tweak the model, the fracturing model, to produce the same production that I got and that I measured in the formation in the field. So by the fracture treatment analysis, we match the pressure during the treatment with the pressure with the design pressure. Just change the design parameters. Like, for example, if the field guys increase the rate, so I need to increase the rate in the model, and if, for example, they got frictions difference number than what I designed, so I need to change the friction numbers in the model to match the pressure with the actual pressure. So the fracture geometry from the fracture model and the fracture software is the match, is the same geometry that's created in the formation. Then when we go to the reservoir simulation, the production should be the same as if the formation properties is accurate. So the production should be the same during for the model. So I match the pressure for the fracture simulator, then take the fracture geometry from fracture simulator to the reservoir simulator, to get the production match. So if it matched the production and pressure match, so this fracture geometry is created by is what is created, and this is what causes the production in post-fracture production. Another way to this is a way to get and to understand the fracture geometry, and mainly the fracture half length and the fracture conductivity. Another way to measure the fracture height is by temperature log. Simply, if we measure the temperature profile in the formation, if we have a static, we simply as a static well bore with static fluid, we measure the temperature in the formation in the well bore. Then we starts to circulate the well. After we circulate, and while we circulate the well, we measure after we circulate the well, we measure the temperature, so we can understand the if there is a channel or any anomaly in the formation. Then bump hydraulic fracturing, and as soon as possible run with temperature log to measure the temperature in the well bore, and we can get the fracture height and and measure the height of the fracturing that the fracturing fluid covered using the temperature log by measuring the temperature during the warm up, because more fluid will be slower than the formation. If I have a formation without fluid, it will, or less fluid, it will warm back quickly, quicker than the formation that has invaded by the fracturing fluid. But the temperature log, it has the quality of temperature log depends on the thermal properties of the formation. If there is anomalies that can cause misinterpretation or not, the wellbore hole, open hole diameter, and the thickness of cement, there is some challenges in temperature log, but it can be used to understand the height of the fracturing propagation that happen in the formation. Another way to understand the length of hydraulic fracturing and measure the length of hydraulic fracturing is by microseismic. We drill a well, observation well. We set geophones in the observation well, and during the treatment we measure the microseismic events. Simply, microseismic is like you hear what you hear the fracture in the formation, and to know where is there's a fracture in the formation, the points that cracked in the formation. So the result of microseismic events is a cloud of cracks that happen in the formation, and is detected by geophones in the microseismic well. It has a lot of limitation, like the distance between the monitoring well and the operation well, and the distance of the depth of observation well and the treatment well. And there is some limitation, and there is a development in technology with time. But the main idea is that you hear the voice, or you hear the cracks that happen in the formation, and compare, and once you get the cloud, you can figure out this area or this length is covered by the hydraulic fracturing. Another important point, pressure transient analysis get the effective propped half length, but microseismic get the total half length. So if you crack the rock and you didn't place a propant in it, and this crack is closed, it can be detected by microseismic, but it's not efficient because there is no width in this length and is not efficient in pressure transient analysis. So, and pressure transient analysis doesn't count for this length, which has no contribution in production. So the microseismic can give you overall the maximum half length created in the formation, but pressure transient analysis get the effective prop half length that created in the formation. Another way to understand the contribution of each frac stage in multi-stage frac to pump a radioactive tracer or chemical tracer with hydraulic fracturing stages to then produce the wells, produce all stages and measure the contribution of each stage based on the contribution of each chemical in each stage in the production flow. So it can indicate the relative conductivity between frac stages and the contribution of frac stages and the fracture geometry relatively between stages. Another use for the tracers is to pump the tracer with hydraulic fracturing and run with gamma ray log, but it's rarely used due to environmental issues and due to safety issues for the frac crew and logging tool crew. So you can, from the radioactive, from gamma ray log compared to pre-frac gamma ray log, we can understand the height of hydraulic fracturing, but it's now really used by the industry. The main to understand the fracture height and measure the fracture height is temperature log, and to get the fracture half length, the total half length we can get by microseismic, and for the effective fracture geometry and the effective fracture half length and the effective fracture conductivity can be measured using the pressure transient analysis and pressure and production decline production data analysis with fracture treatment analysis. So that's simply the ways that we evaluate a job. We need to evaluate the job during the treatment, like using Nolte-Smith technique, and another technique, and the after job using microseismic or temperature logs or pressure transient analysis or production data analysis with the fracture treatment analysis. And that's the main evaluation procedures that we need to do in field and in the office to evaluate our fracturing job. And thank you.
Thank you, Engineer Muhammad, for your time and efforts conducting this interesting session. So we have just some questions into the Zoom chat. We hope that you can answer.
Okay.
So the first question is asking, what is the best geometry for fracture propagation?
Okay. To understand the best fracture geometry for the best fracture geometry for your reservoir, you need to understand your reservoir in a better way. So, for example, if you have a high permeability formation and you suffer from new bore damage, so the best fracture geometry is wide frac and short frac. So you need only to treat the well around, the area around the well bore. If your reservoir is tight and you need to enhance the production from this tight reservoir, so you need large frac, but you don't care a lot in fracture conductivity, because any fracture conductivity will be more than the formation permeability. So any sand or any proppant type will be enough. So based on the formation and the properties of the formation, which is the drainage area and the formation permeability, you can get the best fracture geometry. For generally for high berm formation, you need short frac and you need high conductive frac. For tight reservoir, you need for tight reservoir you need high fracture half length, and you don't care about the fracture conductivity, so you don't care about the width and the proppant permeability. That's general concept, and it can be defined case by case.
Okay, thank you. Another question is asking how we can estimate the pressure transient response for a horizontal or a hydraulically fractured well at an arbitrary orientation in an anisotropy reservoir.
Okay, for
He is
unconventional,
asking, he has asking about the pressure transient response, how we can measure it for horizontal well at arbitrary orientation in an anisotropy reservoir.
Okay, so for during in horizontal well, and there is unconventional frac, the type of frac is not simple as a bi-wing frac. It's what's created is a matrix of what's created is a network of hydraulic fracturing. So you have a lot of fracture propagation in multiple directions, and you create a mesh of or network of fracturing. So in this case, it's a bit the pressure transient analysis may be very hard to interpret. So the unconventional industry came in the last 10 years with the concept of transient analysis in rate. So you can conduct rate transient analysis to understand the fracture, the average fracture half length, the average of the fracture that's created in this network, and the average width based on the rate transient analysis. Pressure transient analysis may be not enough, and maybe you may get inaccurate results because of difficulty of fracture propagation.
Okay, thank you. The last question is asking, how do we manage the temperature and the fracture conductivity, considering the formation geomechanics?
Okay, simply we measure the base temperature profile in the well during the static and during the circulation to know the anomaly in temperature profile in the well. Then after hydraulic fracturing, we compare between these two baselines and the temperature profile after hydraulic fracturing. The difference is related to the fracture height covered by the frac. Does the formation geomechanics affect on this interpretation? It shouldn't, because we simply measure the difference due to invasion of the fluid in the formation. This invasion happened due to the fracturing or happened due to there is a channel. It doesn't matter. because we already circulated the well, and we know the channel, the presence of channel or the baseline during circulation, and just after the frac, the is compared to the what before frac, and so the difference is what happened due to the frac. Okay, and the quality also, if it can be affected by the thickness of cement, the diameter of open hole log, and the presence of temperature anomalies in reservoir and the reservoir geothermal properties, and many factors. But simply we measure the warm up of each, because the fracture deformation is take a lot of time more than the non-fracture deformation.
Okay. Thank you, Engineer Mohammed, for this interesting webinar. I think that one of the most interesting webinars that we delivered. So thank you again for your time and effort conducting this interesting session. Also, I want to thank all the attendees that attended our today webinar, and I hope that you benefited or get the information that you hope. Also, I would like to remind you by the 2 upcoming courses that we are having. Hydraulic fracturing. In that course, we will evaluate, we will design, we will know how to design, execute, and also evaluate the hydraulic fracturing jobs. Also, the other interesting course, which will be the boreholes image log interpretation and processing. So if you want to enroll in any of this course, you can register by clicking the links that will be sent into the Zoom chat now. Also, another important note, that if you want to have a certificate for attendance of that webinar, you should fill into the Zoom chat into the link or the form for certification that sent the Zoom chat now. Okay, so thank you all, and you have just 5 minutes to fill into the certification. Thank you all, and hope to good night.